today we're going to start talking a little bit about how heat affects the human body. And really, what we're doing on this first discussion here is really just talking about things that are going to influence either heat buildup or heat loss out of the body. So we are going to be dealing with what's called, basically, it's an equation that's looking at pretty much heat loss and gain. Again, humans have a normal body temp of about 98.6, somewhere around that region. We'll see. Again, how we interact with a particular environment is going to be really important to, do we gain heat, do we lose heat, and what are the avenues by which we can do this. So we're going to be working with what's called the heat balance equation, and we're going to see it has a number of different parts to it, which we're going to work through. So how do we lose heat? How do we gain heat? If we can't get rid of all that, does it lead to hyperthermia or hypothermia? Again, definitely the human environment. There's going to be a lot of things that influence this. And really, again, what happens when we can't maintain that balance? So normal body temp, like I said, is around 37 degrees Celsius. Again, anywhere from 97 to 99 degrees. A little bit higher if you're actually looking at the core body temp. Usually when you're taking it by the mouth, that's going to be a bit lower. Rectal temp is the one that usually do it. That is the most accurate of core body temp. There is other ways to do this. Certain labs and other stuff like that, they will do what's called an esophageal probe, where they will take it and it actually goes up your nose and down into your esophagus as a temperature probe. Again, your skin a lot of times is what we refer to as the shell temp. This is a little bit more variable. Again, with everything going on with COVID right now, this is one of those reasons the little heat guns that are just kind of going on your forehead, they may not be the most accurate way to actually temp somebody. They're looking at more of skin surface temp and not actual core body temp, where anything that is actually looking a little bit more at core temp. So the ear ones are probably going to be a little bit more accurate. So heat balance is really this idea that the body needs to kind of maintain some type of level of homeostasis between the environment and the actual internal level of heat in the body. So really what we have to do a lot of times is, if we're in a warmer or colder environment, that is going to affect this heat balance. And it's really a balance here between how much heat do we produce and how much heat can we lose. And again, in conditions where there's more external heat, a lot of times this gets into, can we dissipate enough heat from the body, where in cold environments a lot of times it's, can we generate enough heat to not have that environment have a big effect on us. Again, if we are not able to balance this out, we're going to have a gain of heat or a loss of heat from the body. So again, heat production is thermogenesis, heat loss is thermolysis. And again, we are homeotherms, meaning we have a core body temp somewhere around a set point, so 37 degrees Celsius plus or minus about a half a degree. So it's about 1 degree Celsius of change. So we're looking at a couple degrees of Fahrenheit either direction of that. And again, this is a range, not an actual single set point. So hormone levels, metabolism, other things like that are going to have an effect on this. And again, we are going to fluctuate within this range. And again, it's only when we get out of this range that we are going to have more things happening to try to bring us back in here. So we actually have other factors getting kicked on and bringing this about. So again, you can kind of see, looking at the kind of image here, it's really the core that we're talking about, that maintaining this temperature. And if you've ever been in really cold environments before, sometimes your hands or your feet will get cold, or your ears or your nose will get cold before the rest of your body. And again, that's because in cold environments, we try to maintain that core temp, and a lot of times we will actually start shunning blood away from those areas that are causing temperature loss. So again, looking for that core temperature. And one of the things as we get into this stuff a lot more, we will talk a lot about the core temperature versus the shell temperature. Shell temperature can honestly be a lot more variable. We can get skin surfaces that can get quite cold where the core temperature is being maintained. So this is what we're really going to work around here. This is what is referred to as the heat balance equation. As you can see on it here, there is a ridiculous amount of letters on this. And S is really what's going to be changing on this. So that's going to be the big thing. That's if that's a positive or negative, that is heat gain or heat loss on this one. So we can see there's a number of different things here. Metabolism produces heat. That is the M in this one. If we're doing any work, rate of mechanical work with this heat, that is going to take away from that. That's usually pretty much 0. So that rate of heat production is going to have to be balanced with these other parts, which are conductive heat loss. So conduction is really one surface touching another and moving across that. So if you touch a cold piece of metal, you might lose heat to that cold piece of metal. That's conductive heat loss. C is convective heat loss. Convection is air currents or fluid moving past you. So either air or water a lot of times are how we're going to have convective heat loss. Radiative heat loss is just if you're standing here, you will lose heat to the environment, radiate it out. Sun is doing that and radiating heat to us. And then the last one here on these is going to be evaporative heat loss. So when you are actually sweating, that loss of heat into evaporating the sweat is a way we can move some of this heat away. The one thing I want to say on these ones, we're talking about these always being heat loss on this particular thing here, but really any of these things could be a heat loss or a heat gain in terms of this. So like radiative heat loss, we're talking about being on the skin, but you can also have radiative heat hitting your skin that's going to increase this. So these numbers can be a negative or a positive going away from this, depending on if we are, again, if you're in a hot environment and there's warm air blowing on you, you're going to have convective heat gain. If you've ever touched a hot pan, that's conductive heat gain, not loss. So all these things can kind of work in both directions. So ideally what we want to have balance out is the amount of heat production we're generating balance out with the rest of these in terms of what we're losing, and effectively neither lose or gain heat. So we want this numbers right here to balance with these other parentheses, and that would mean that we are not having any gain or loss of heat. Again, when the production that we're doing does not match with these one, or we're gaining more heat here, what that means is this number is going to have to change to balance this equation, and we'll either gain or lose heat. So again, when it comes to the metabolic heat production, so now we're going to walk through each of these variables a little bit. So when it comes to metabolic heat production, every chemical reaction we do, any muscle contraction, these are going to generate heat. Again, most of our reactions are not particularly efficient. Somewhere, maybe good ones are 50% efficient. Most of them are quite inefficient. So a lot of our chemical reactions, our body lose heat as a byproduct of this. This heat is transferred into the body, and it's what helps maintain our core level of heat. Very rarely do we have any heat going towards actually doing mechanical work. So that is usually a 0 in these ones here. We're not having heat on the body go to mechanical work. So again, with what we're talking about on this one here, if we're generating heat, we need to maintain a balance of heat. So these different other variables, if the environment is too cold, we are going to need extra heat to help balance out that equation. If the environment is too warm, we need to dissipate heat to get rid of this. So what we need happening is all those mechanisms of heat loss, we need them to match up with the amount of heat that we're producing. So conduction, like I said, or the K on that equation, this occurs when two surfaces come into contact with one another. A lot of times they've talked about if you're in really cold environments, you get caught out in the weather. A lot of times people would say huddle together for heat, or they talk about kind of that kangaroo care with babies, the skin on skin contact. That is going to help with conductive heat gain in that case. This again when two different surfaces of differing temperatures contact with one another. Again, depending on what these surfaces are, we're going to have certain ones that are better conductors of heat, such as metals, water. Our muscle tissue is a very good conductor of heat. This is part of the reason if you're in cold air, you can be in much colder air and not lose a ton of heat, because air is not a particular good conductor of heat. where if you're in the water, I think everybody's kind of realized this, if you're in kind of just slightly cold water, I mean, it can be below zero outside and you can be out there for a little bit and not be freezing, where if you jump into water that's 35 degrees Fahrenheit, you're going to be hypothermic rather quickly because water is a much better conductor of heat. We also have different substances that are good insulators. Air, again, being one of those, at least in terms of our body, our adipose tissue is going to help with maintaining this core tissue because we can't conduct as much heat out to the surface of the body in cold areas when we have a little bit more fatty tissue in the body. The other thing is we do have any air that we trap inside of clothing is going to help with reducing that conduction of heat to this away from the body. So a lot of times this is why in hotter environments you're generally not going to wear as much clothing or long clothing because it is going to help hold that heat in. Ideally in cold environments you wear more clothing that's going to trap more of that air and help prevent that heat loss. Again, conduction, it's not probably our biggest factor when it comes to the body, with the body and heat loss or heat gain. Again, a little bit through the air. If you happen to fall in water, it's going to be a much bigger one. Body heat, like I said, being conducted from skin to clothing and that type of stuff is, again, not going to be the biggest one in here. We do have it happening within the body, so conductive heat from the core of the body to the shell of the body, through the muscle, through the adipose. That is where this is a lot of times more key. But it's, again, generally conducting the heat from the core to the surface, and then it's a lot of times more of evaporation, convection, or radiation that we're really dissipating more of this heat from the body. Factors that will influence is if there's a bigger difference between these two different conductive surfaces. So if you have something that is your body temp and then something that's very cold, you're going to have a bigger heat exchange than if those numbers were closer together. The more surface area we have that is in contact with another thing here, as well as shape of the body to the air, any of these things are going to help increase conductive heat exchange. The more clothing you have on the body, it's going to decrease the surface area exposed, so we would generally have less conductive heat exchange to the environment when you have more clothing on. And again, anything that has a better thermal conductivity up to it, so like we were saying before, things like metals, water, muscle tissue. If you have more muscle tissue and less adipose tissue, you are going to have more conductive heat exchange than somebody that has more adipose tissue. So anything that limits the distance between these two surfaces, again, going to help out with that heat exchange. And again, anything that increases the core temperature is going to increase conduction to the shell from that. So if you're generating more core heat through exercise, it's going to help push more heat to the surface. And again, as I said before, these things can work in both directions. A lot of the change we're talking about here about increasing the conductive heat exchange, if the opposite things happen on those ones, it would decrease that conductive heat exchange. And again, if what you're talking about here is warmer than you, it's going to get conductive heat gain, versus if the surfaces are cooler, it's going to be conductive heat loss. So again, each of these factors that we're talking about can generally work in both directions. And this just kind of shows you the idea with the block of wood, not much going to happen with this, but it's those two surfaces in contact with one another. Again, of all the ones that we're talking about here, this one is usually the least important when it comes to thermal regulation. And like it says here, this is most important when we're talking about exposure to extreme environments, really hot or really cold environments, and a lot of times in environments that are going to have good conductivity. So falling into water, even standing still in water, you will lose a lot of heat to conduction. The other one we're going to talk about here and then move on to another show here is going to be convection. So convective heat loss or gain is when at least in terms of conductive heat loss, is when molecules are moving from a warm object to a cooler area, usually by some type of fluid. And when we're saying fluids, air counts as a fluid in this case, surrounding fluid, so the air or the water. Like it says here, the heated fluid expands, becomes less dense, and rises, taking the heat away from the body with this. The area right next to the skin then is replaced by cooler, more dense fluid or air, depending on if we're talking about water or air. And again, the same process is going to be repeated. So it's a way we can lose heat that way in terms of convective heat loss. Again, this can happen the other direction. If you had a much warmer fluid come to the body, you could have convective heat gain. More heat getting to the body gets transferred to the body. That stuff falls away, and then more heat goes to the body, again, if the environment was hotter than the body. This also happens in the body as well when we talk about warm blood moving into a cooler area, being cooled. This flow of blood through these tissues, and we've talked about this a lot of times in A&P before, in things in the male, and like the testes, and cooling the blood that's going down to the testes, you have a countercurrent heat exchange going on there. And again, because if we get into something as a better conductivity, convective heat loss, again, for water would be much greater than air, because water is much more dense than air, so it's gonna pull more heat away to that density before that is heated enough that it moves away from the body. Again, two main types of convection. You have free convection. Again, this is really slow flow right here. So if it's just standing here and this is you heating up that environment, and then it freely just kind of heats up a little bit and moves away. Where a forced convection is moving fluid at a higher velocity past the body. So if you think about why, well, a good example would be this is like a little fan when it's warmer out. You're blowing air at you, but because you're moving air at you, it helps to cool you off. That is an example of forced convection. Or if you were in some type of spa and moving cold water past you, it would help cool you off a little bit quicker. Like, so again, this forced convection is going to lead to, again, if we're talking heat loss, a greater heat loss than free convection. Again, factors that are going to influence this and increase this convective heat loss, some of these are going to be very similar. So one of these, the differences in the temperature between the two mediums, the bigger the temperature difference, the bigger the convective heat loss is going to be to that. Whatever the medium that we're circulating to, if that decreases in temperature, that will increase the heat loss. Is almost everything we'll talk about with heat balance. More surface area is going to lead to greater heat exchange, and in this case, if we're talking heat loss, can lead to greater heat loss. Again, more exposed surface of the body, decreased clothing covering, which will increase that surface area available for that heat exchange. Again, anything that messes with that is going to change the conductivity. So water versus air, you're always going to have a greater loss in water because there is more thermal conductivity in the water. And again, if that fluid or that medium is is more dense, it's going to be able to draw more heat away from the body. And again, because conductivity is greater for water than air, we can definitely see a lot more loss there. And like it says here, increases in precipitation would increase that convective heat loss. But again, it's going to depend upon temperature, air temperature relative to the skin temperature. Again, and the other thing you've kind of probably felt this before too is on a windy day at the beach versus on a non-windy day at the beach, you get out of the water, you're having some of the evaporative heat loss. If you have the air blowing across it, it actually increases that convective heat loss, increases the evaporation rate as well, which we'll talk about in the next one. That's part of the reason you will a lot of times on a windy day be a little bit colder when wet versus dry. So again, decreases in insulation of the clothing when wet. It's gonna be more of an issue. You're gonna have more convective heat loss because you have a higher conductive medium helping to move that heat away. at altitude, you have a less dense surrounding of that. Air density decreases, so convective heat loss decreases. And again, the more airflow, the more turbulent it is, the greater the convective heat loss. And also, the faster that fluid is moving past you, the more it can draw away, because what's happening is that fluid is always being replaced by a cooler fluid. So there's more ability, there's a bigger gradient for you to lose that heat. And again, the same thing within the water as if you dive down deeper and you get increased pressure, you have increased density of water. Because that, as that density increases, again, that convective heat loss as you're moving through it can increase. One of the interesting things with this one is like falling into cold water is a good example of convective heat loss. You have to be careful with this sometimes, in that if you were to fall in cold water, if you're not particularly close to shore, you're actually better off staying put and warming up the water around you and trying not to swim through it. And that as you start swimming through it, the faster you swim, the greater the convective heat loss. And if you're far enough away, you will actually get hypothermic before you can reach the shore. Again, if you're exercising, you're going to have a greater core temperature, which again is going to increase that flow to heat loss out of the body. And again, everything that we've talked about here, if it's going the opposite direction, that would lead to heat gain versus heat loss. So again, I just want to keep reminding everybody, the factors we're talking about here, if they go in the other direction, you can have convective heat gain. So a denser fluid that is warmer than the body flowing past the body is going to lead to heat gain in the body. So, and again, just remind everybody, convection is that movement of an air fluid past the body, which is going to take heat from the body and take it away. Surface temperature of the body, like I said, usually greater than the surrounding air, and that is that air being moved past it is going to be that convective heat loss. So when we really talk about being in water, or in water that's colder in the body, this is about 100% of what your heat loss is going to be. Is almost all the convection. Normally in the cold environments, it's a good portion of this. So in the air, about 70 to 80% of heat loss in the cold is going to be this convective heat loss. So what we'll do on the next one here is we'll talk about some of the other variables on this, and then, like I said, we'll move on to actually talking about accommodations to heat as well as adaptations to heat in the next week or so here. I will talk to you next time.